it short for the online audience. And again, welcome to this session. I actually did this to this before to the in-class audience, but I realized that microphone wasn't on. Sorry about it. So today's speaker is going to be Runan, and she's actually a graduate research assistant, and she's on her way of obtaining a PhD degree. Today, she's going to talk about her dissertation work, including how to integrate econometric methods and machine learning models in understanding traffic safety risks and predicting crash patterns. Without further ado, Runan, please take over. Thank you.
Hello, everyone. Hello, everyone. Thank you, Doug Lee, for the introduction. Can everybody hear me, right? Everybody can hear me, so I'll present.
Can you share your screen?
Sure. I'm working on that. Okay, everybody can see my screen and my slides now, right?
Yes, go ahead.
Okay. Hello, everybody. Thank you, Doug Lee, for the introduction. I'm sorry I cannot be on USF campus today. So I'm Runan Yang. I worked in Qatar for 4 years and 8 months. Today is a summary of the work I've done in Qatar. And my presentation is titled High-Risk Traffic Crash Pattern Recognition and Identification using Econometric Models and Machine Learning Models. So the 3 topics will be covered in my presentation, which are crash frequency modeling, crash severity prediction, and crash hotspot identification. And the first study, as you can see, the title is Nighttime Crash Risk Estimation Considering Lighting Illuminance. This study will quantify the safety effects of lighting illuminance on nighttime crash frequencies along roadway segments. And the second study will focus on the motorcycle crash severity prediction and understanding its causal effects on motorcycle crashes in horizontal curves, especially improper actions from motorcycle rider and vehicle drivers. And the third one will help us to identify the high-risk crash spots before crash occurrences using the new model and data. So in today's presentation, I'll introduce my research topic by topic thoroughly. So first of all my research in Qatar is about traffic crash modeling. So what is the traffic crash? So a traffic crash or a traffic collision, or motor vehicle collision is when a vehicle hits another vehicle, person, or object. Pedestrians, animals, roadway debris, or other objects may be involved. Traffic crashes often result in injury, death, and property damage. Regardless of notable improvement in the field of vehicle technology and roadway engineering, globally, traffic accidents are one of the leading causes of human death and injuries. So according to World Health Organization, WHO, more than 1.35 million people died every year due to traffic crashes. So let's focus on the statistic results lately in the US. So based on a CDC report on COVID-19 takes more children than flu, but it's far less than car accidents. So this report by CDC pointed out children are 9 times more likely to die from a car crash than COVID-19, based on the data in 2019 and 2020. Roadway safety is partially a matter of roadway design. So for us as traffic engineers, ideally, these roads should be designed for the safety of all road users, including pedestrians, cyclists, motorcyclists, and all other users. So this infrastructure measures such as footpaths, cycling lanes, safety crossing point, and other traffic measures can help us to reduce risks and prevent the injuries. So at first in my research, I identified 2 high-risk traffic crash circumstances. The first identified high-risk crash circumstance is nighttime crash. You may think about that less exposure during nighttime may cause less crashes, but it is reported that 51% of fatal crashes and about 30% of injury crashes occur at night, with only about 20% of vehicle miles traveled, which is a measure of exposure. So especially for pedestrian crashes, 3/4 of pedestrian fatalities caused by nighttime crashes. So nighttime crash is one of the high-risk circumstances identified. And similarly, motorcycle crash on horizontal curves is also identified as one high-risk circumstance. The Texas crash facts mention that motorcyclists experienced fatal and severe crashes 8 times more than non-motorcyclists on the horizontal curves. So a lot of previous study also proved that human errors are the primary cause for crashes because driving or riding is a complex task which need to be trained and practiced a lot. And for the third topic about crash hotspot identification on the roadway network in Florida. So do you guys know Florida is one of the top 10 states with the most fatal motor vehicle crashes in recent years? So especially in the year of 2020, Florida ranked number 3 with over 3,000 fatalities. And also in 2020, over 400,000 crashes occurred, and about half of them are injury crashes. That's the reason why Florida is selected as the study object in this research. So if we can predict crash locations in advance means before crash occurrence, we are able to take some proactive strategies to reduce these risks. Let's move on to the first topic, safety effects of lighting illuminance on nighttime crash frequencies along the roadway segments. So I will introduce research questions, method, modeling results and discussion, and conclusion. First thing first, the research gaps existing. So, well, most of the existing studies in nighttime crash focus on the safety effects on the roadway intersections instead of segments. But the truth is, 40% of fatal crashes occur on roadway segments. Segments are dangerous as well. And on the other side, most of those studies use the lighting indicators instead of detailed lighting photometric measures. So those indicators I am talking about include indicators like whether there's lighting device or not on this facility, or indicators like whether the lighting condition in this facility is uniform or not. Well, field study really consider the detailed effects, especially the lighting uniformity. And also, the data they were using is not that accurate and precise. So more precise lighting data need to be used in this kind of photometric lighting analysis. So in this study, I will select appropriate lighting measures for photometric characteristics and also develop models to quantify their effects on crash occurrences. And I'll use 2 approaches in the modeling part. Before I talk about data and model, I would like to go through this lighting illuminance measures. So usually we will use lighting mean to represent the average level of illuminance. But for uniformity, usually in engineering practice, ratio-based measures are more popular. So those ratio-based measures, for example, maxima over minima or average over minima, are widely used. And this ratio-based uniformity measure could not eliminate the influence of extreme lighting points, and it could not capture the real lighting patterns which affect driving. Let's take an example. So here, as shown in this figure, is it clear for you guys these numbers? But anyway, like it's shown in this figure, the uniformity on this roadway segments is defined as if we use maximum over minimum ratio, this will be 15, which is 1.5 divided by 0.1 here. The maximum point is over here. But we can see this minimum illuminance point is far away from this maximum illuminance point. But this change from the minima to this maxima would not influence driver's vision that much. The real pattern which influences the crash risk is the change from this relatively lower lighting zone to this high lighting zone. So visual-based uniformity measure is not a accurate and precise measure, while standard deviation considered to be a more precise measure for uniformity. And about the data, so the lighting data I use is collected by Cutter team through the 5 years and using the advanced lighting measurement system. You can see it from this figure how we collected the lighting data. This can provide high resolution lighting data, and the lighting points we used for measurement and collecting data is generated every 10 feet along the roadway. So based on that lighting data, totally 440 roadway segments with street lighting were identified based on detailed conditions. And 4 years of historical crash data from 2011 to 2014 were collected and matched with their roadway segments and corresponding lighting data. These crashes could be divided into 2 groups based on their time. So totally 3,318 nighttime crashes and 9,755 daytime crashes are matched on these roadways. And the roadway geometric design and traffic information used here are also matched on these roadways. These features including traffic features like annual average daily traffic, AADT, truck percentage, T-fact, roadway length, and land use information. So here is a table gives you descriptive statistics of the variables I'm using, their distribution, and more information. And I use random parameter negative binomial model to address the heterogeneity. So it allows some variables to vary across different observations. And in this way, this model structure can account for the heterogeneity from one roadway to another. And the expected night-to-day odds ratio is also used to eliminate the influence of confounding factors. So to be specific, so in a roadway segment, the crashes occurred on day and night may share some characteristics, which is related to roadway design or conditions. While this night-to-day ratio could control the variation in nighttime crash risks that are unrelated to lighting by incorporating with daytime crash risks. So the crash modification functions for illuminance mean, the average based on expected night-to-day crash ratio are shown here in the red line. And this red line suggested that increase in mean horizontal luminance tends to decrease the relative risk of nighttime crash occurrences significantly on roadway segment, as we expected. But the quantitative results is shown here. So by using this result, you can easily find how much the crash risk will change if you change the lighting condition from different values. And also from this figure, we can compare it And notice that the effects of illuminous mean is greater in its lower zone than in its higher range. And this is CMF for illuminous standard deviation, which is a uniformity measure. And it is easy to tell increase of standard deviation value are more likely to increase nighttime crash frequency. It's intuitive, like a high standard deviation value representing more changes of constructing high and lower lighting patterns. And this changes is more likely to cause human eyes to take time to adopt new lighting conditions. And drivers' vision may weaken during this adjustment period. So this may increase the driving risks at night. Those are all the modeling results. But besides that, based on the data I have used, I also found the standard deviation is strongly correlated to the mean of horizontal illuminance. And while the random parameter negative binomial model I used in this before could not distinguish the safety effects of average lighting level from lighting uniformity. And this correlation issue is a significant limitation in this modeling part. So how can we solve the correlation in our model? So to specifically quantify effects of lighting uniformity individually on nighttime crash risks, we adopted matched case controls method from biology and psychology into transportation, especially into crash modeling. So this matched case control approach is usually used by controlling other factors in similar conditions and explore the difference between the control group and the treatment group. The 4 steps of a successful matched case control approach are shown in the slides. First, these roadway segments are divided into subsections with a fixed length. Here we choose 600 feet. And these segments are our study object. And the second step is to label them. And the nighttime crash data was matched with each subsegment. So those subsegments with at least one crash in a given year are called cases, and the subsegment without any crashes are called controls. And the third step is to match confounding factors based on correlations. So those correlations is shown in this figure. AADT, annual average daily traffic. We noticed the AADT and the number of lanes are correlated with illuminous measures, and including mean and standard deviation. The fourth step in this study is to develop a conditional logistic regression model to quantify the effects of unmatched factors. So in this study, totally 6,440 subsegments are identified, and illuminous mean, as I said before, is a confounder for uniformity. But also, this variable year, crash year, is usually related to driving behavior, vehicle safety technicals, roadway maintenance, and this environmental conditions. So the matching of this study, the matching process is conducted for each year. Also, I want to say it is impossible to match those illuminous mean at exact value. So those mean values are categorized into 4 levels, which are less than 0.4, 0.4 to 0.8 foot candle, 0.8 to 1, and more than 1 foot candle. Those variables, such as roadway functional classification or speed limit, are highly correlated with illuminous mean, as I showed in the previous page. So this is pretty easy to understand. We usually see that a major arterial in urban area with better illuminous condition and with more lanes. And so those variables I mentioned are not considered in matching. So later in this study, I only used illuminous mean and year for this matching process. And the descriptive statistics of the data used are shown in this table. And a case is matched with one control just because of the smallest number we can do with this data. The observation here is similar to the crash modification function CMF I defined before, which is how much the crash risk will change with the change in illuminance uniformity level change. And this table is the model results, and the lighting uniformity is aggregated into 4 levels, and standard deviation less than 0.2, which is very good uniformity, and level 2, 0.2 to 0.57, level 3, 0.57 to 0.7 are intermediate uniformity conditions, and level 4, very poor uniformity conditions with the highest standard deviation, which is more than 0.7. Those thresholds 0.2, 0.57, 0.7 are all determined by the data, by the distribution of the standard deviation, this variable, and the variable significance. I perform this model, develop this model. So as shown in this table, the coefficients for standard deviation levels are all significantly positive, and it becomes larger with increase of standard deviation level, which means compared to the very good uniformity condition, increasing in standard deviation levels means worse uniformity is more likely to trigger nighttime crashes on roadway segment. And in these studies, I use standard deviation other than visual-based measures to detect the effects of extreme values and to capture the true pattern influencing nighttime crash risks. Also, we learned that the nighttime crash risk is 2.42 times more likely to occur in a roadway segment with poor uniformity than a roadway segment with very good uniformity. So that's for the first topic. Let's move on to the second part, improper driving action analysis in motorcycle crashes on horizontal curves. So previous study focused on finding the factors contributing to the crash severities a lot, but how these factors would influence the severity outcome has not been fully understood. So it means it will directly affect the severity, or it will indirectly affect it through some other variables. So in this study, this new model structure will help us to develop the cause and effective chain to better understand the causation in motorcycle crashes. So in this part, I'll answer these research questions. So what would be the factor causing motorcycle riders' severity outcome in a crash, and how? Specifically, the question is, for a given motorcycle crash on horizontal curve, what would be the predictors for whether the rider injury severity outcome is fatal or not? Or it is not the factors which cause the fatal motorcycle crash occurrences on horizontal curves. From the title, there are 2 terms I would like to explain. The first term is horizontal curve. So a horizontal curve is defined as the section between the point of curvature and the point of tangency, plus a 300 feet buffer for each end. In this study, I specifically want to know how some curve alignment design characteristics affect rider crash severity. So for example, the curve radiance, which means how sharp the curve is. And the other variable I would like to explain, the other term I would like to explain is improper actions. And this variable is extracted from crash report about the contributing factors to the crash for rider and driver. So this that means their pre-crash actions. So these improper actions mentioned here include speeding, careless driving, failing to yield right away, driving into the wrong line, following too closely, improper passing, etc. Oh, I haven't mentioned the motorcycle at fault. So formal studies usually use motorcycle at fault status, which is the party taking the major responsibility in the crash. But this information was usually judged by the investigation officer, which is not that accurate in our crash database. So especially with the fatal crash with rider died. In this case, the other party will automatically become at fault side. But possibly the fact is both of them are taking improper actions. Let's see, one is speeding a lot and the other failed to yield. So compared to at fault, this study I used improper actions because it can provide more detailed information about both rider and driver about their pre-crash actions. Here's just descriptive statistics. I just want to highlight the dependent variable I used and the curve characteristics variables I chose here. And I did use some other variables for my modeling as well. And about the dependent variables, the injury severity outcome, I choose rider fatality indicator. So usually motorcycle rider is the one with the most severe injuries in a motorcycle vehicle crash. And also, you may ask if you know the crash report, how they recorded the injury severity is usually 5 level. But in this study, I only use this binary because it's more clear for us to understand and to build the cause-effective chain to understand the causation in motorcycle crash. Then we use 5 level or 3 level injury severity. And the other two, this is two dependent variable. The other two I use a rider improper action indicator and driver improper action indicator. And I developed the two models, one for rider and one for driver. And the recursive bivariate Probit model equations are shown here. So the recursive structure is highlighted. So here, improper action is the outcome of some pre-crash behaviors, and it's also a predictor for rider severity outcome. And also marginal effects, which measures the direct and indirect effects of these pre-crash actions on injury severity outcome in the models. So the calculation equation is shown here, and it is a difference of two probabilities of fatality indicators. So the changed variable, the independent variable, could be divided into two types, continuous variable and dummy variable. The marginal effect captures the changes in fatality probability change with a unit change in continuous variable. For example, this continuous variable has value change from 2 to 3. And for dummy variable, for example, like daytime indicator, this variable taking the value of 1 or 0 based on the crash time. And the marginal effects capture the probability change when this value of this daytime indicator changes from 0 to 1. And a figure about the cause and effective chain I built about rider improper actions and rider severity outcome is shown here. So theoretically, some contributing factors like crash, curve, and roadway, environmental, traffic, or vehicle information will directly affect rider severity outcome, which proved by a lot of previous studies. This is shown in the yellow line. But here, others, we actually found this. There are some variables which first impact the rider improper actions, and then it will indirectly affect rider fatalities, because the improper actions are connected to the rider injury severity outcome. And the marginal effects of rider model is shown in this figure. So I found that moderately sharp curve, as I mentioned before, and the flat curve is more likely to lead to rider fatality. And it's not surprising that rider themselves, their physical defects and impaired riding tends to cause both rider improper action and rider fatality. So while factors like paved shoulder, rider insurance, and helmet use will influence riders' improper riding actions and also indirectly have effects on rider fatality. This is what we found from this model, and the driver model are similar to this one and the model results. So through the two recursive bivariate Probit model, I actually found moderate sharp curve and flat curve have direct impact on the likelihood of rider fatality in both of the models. And compared to like really sharp curve, this moderately sharp curve tends to increase the likelihood of rider fatality by 3.3% based on rider model. And the flat curve tend to increase the likelihood of rider fatality by 3.5 based on the rider model. And also the magnitude of indicate and joint effects in rider model are significantly higher than those in driver model, which implies that this cause and effective chain I was talking about for riders is superior to the chain for drivers in a motorcycle curve related crash. Yeah. Then let's move on to the third part, and roadway crash high-risk hotspot identification. So about crash modeling and analysis, I talked in the other two topics. The majority of research focuses on the microscope roadway facilities, which are roadway intersections or segments. But this may lead to waste. This may waste our limited resources. So let's take an example. Let's see an example here in this figure. In this figure, as I mapped the crash unit and the safe unit, if we use a roadway segment as our object to improve the roadway safety, we will take countermeasures in this green area, which is the entire roadway segment. But the truth is only this yellow square here is the dangerous unit we need to work on. So this will cause some waste in our limited resources. But on the other side, most of the existing studies only use structured data. Okay, structured data is the data which recorded in a standard uniform. So usually the data I was talking before, like crash data, roadway data, traffic data, they just pre-recorded in a standard format for better analysis. So, but nowadays, with improvement in image sensor technologies, transmission big data is trending now. And this big data means multiple data sources, data types from different sensor, different sources like smartphone, GPS data, detector, video, or other sources. So let's see, when you're driving, sometimes you will be distracted by some roadside things, like something like this picture is showing. The gigantic advertisement signs like this, like Core Morgan, which is a concern. Your distraction is a concern while you're driving, and which needs to be considered. But our structured data model could not be considered. That's why in this study, I would like to include image and also the structured data in that. So in this part, I'll develop a combined neural network model, which is a machine learning model, use both traditional roadway and traffic data and also the image data to identify the crash high-risk spot and non-crash safe spot on the roadway network in Florida. So first thing first, the study object. As I mentioned before, I intended to shrink it from the roadway segments or intersections to smaller pattern unit. I selected grid unit in a given size. But how I did it? So I just put Florida roadway network and this roadways. I split it into this grid unit in a given size. So the basic assumption here is this object, this grid unit, can contain the roadway and traffic characteristics. And this can also represent the crash risks information. So specifically, this contains the information whether this area is a crash high-risk zone or not. And here is an example showing how I structured grid unit on a roadway network by matching the basic routes with 2-year crash data. So the latest 2-year crash data, 2019 and 2020 were used in this study. And the points in these figures are the crash points. And as shown here, the crash grid unit, yellow one, is defined as the unit with at least one crash occurred in the 2 years. And the safe grid unit is defined as a unit with no crash occurred in the same time period. And here, our model output is later when you give me when you define a grid unit in the Florida roadway network and using the data, and I can tell you whether this unit is a safe or a dangerous spot. So how I did with the data, to get the list of gray unit, I split roadway by 0.0005 latitude and 0.0005 longitude. To be clear enough, I mapped the roads in ArcGIS based on their location and then split them in a given size. So this could be size 135 feet. So this size 135 feet is chosen because some previous study about high-risk hotspot identification. So basically, this grid unit identification method is becoming more and more popular in epidemiology, especially with COVID-19 cases reported, and this method can use to predict high-risk COVID area. And also this is widely used in criminal reporting and analysis to identify the dangerous spot. So by splitting into unit, I got the list of the coordinates of the point, and then I matched them with their structured data, which is traffic and roadway data, and also I struck their satellite image data through Google Map API. But the total number of these points, so here I mentioned I split the roadway. The total numbers of these points is over 2 million in entire Florida roadway network. So it is impossible for us to get the 2 million something image, especially with get it through Google Map API for this over 2 million points. But also we notice there is no need for us to use the population data to analysis when it's over 2 million. So I randomly selected 10,000 safe grid center coordinates and 10,000 dangerous grid center coordinates. These 10,000 safe points and 10,000 danger points are formed into balanced data. The left side, balanced data. And similarly, I got other two lists with 20,000 safe grid unit and 10,000 dangerous unit to form the imbalanced data. So this way, I can also compare the different model performance and model results across the two data set. So usually we don't actually know the distribution of the safe spots and the dangerous spots. So this way, you can support a starting point for us to understand the true pattern. So later when we know the distribution, or we can probably simulate the distribution, we can get a better idea through this balanced and imbalanced data. And also, yeah, this is how I get the two lists and two data sets. This is showing the other data I matched with this grid unit. Their traffic data and roadway characteristics and image data. So this listed some features in traffic data, as we know as traffic engineers, ADT, truck percentage or type, and also roadway like curve and their roadway design, pavement condition, and functional classification. So this is example of the image data I got. Well, our goal is to develop a model which can use both traditional roadway and traffic data and image data. But I still want to compare this model results with models which use only one data type. So I developed totally 4 models using this available data. The first two models, left side, the green one, the first two models, logistic regression and random forest, are developed using only roadway characteristics and traffic data. So the characters I am talking about here include road curve type, grid type, pavement roughness index, curve type, functional classification, and traffic, annual average daily traffic, truck traffic percentage, etc. The third model, I choose the VGG19, which is the ImageNet model, because it's higher performance in all the image neural network models. So I only use satellite image data to feed this model 3. It's purely image model. But the fourth model I propose a mixed data input combined neural network, which can handle both traditional structured recorded data and also the image. And this model equation and architectures of the 3 models are shown here logistic regression is based on the sigmoid function for a given size. If the function, the probability is more than 0.5, it goes to class 1, which is a safe spot, and class 0, which is a dangerous spot. And random forest is decision trees which vote for the best. And also the VGG19 model here shows the architectures of this model. And the architecture of this proposed combined neural network model is shown in the figure. And the multiple layer perception neural networks are dealing with the roadway and traffic model, which is coded into numeric and categorical data. I also use one-hot coding and the minimum maximum scale to process this features for modeling. And the right side showed here the image data. The convolutional neural network model is dealing with the satellite image through the different convolutional layers. Through the two branches, two individual outcomes are generated, which shows here 8 neurons, and they can be concatenated as a single input, followed by 2 additional dense layers. And also later we'll go to our model output, which is a prediction of the class 0 or class 1. And the Keras functional API is used here to concatenate the output of 2 model branches. To quantify the model performance, 4 performance measures are used in this study: accuracy, precision, recall, and F1 score. Accuracy is the proportion of corrected prediction, so which can be used to measure the overall performance of the given model, the corrected prediction divided by all prediction. And the precision measures the proportion of true positive predictions over all predicted positives, the true predicted positives and the false predicted positives. And the recall is the number of corrected classified observations over the total observations in a given class C. Let's see class C is class 1 or class 0 for a given classes. And F1 score is the weighted average for precision and recall. To simplify it, if I want a better model, I want it with higher accuracy, precision, recall, and also F1 score. So here goes to my model results. This proposed mixed data input model has the highest performance in both imbalanced data and balanced data. And the performance of this model's imbalanced data are slightly better than imbalanced data as we expected. So specifically for imbalanced data model, the mixed data input model can reach 88% in accuracy, compared to about 70% in logistic regression, 80% in random forest, 77% in purely image-based model. But this logistic regression model has better interpretation ability, and this random forest classifier model can help us to know the important features in predicting crash hotspot. So this study first induced mixed data input, which is structured data and image, into crash hotspot identification. And this model can be used to predict high-risk crash spot in advance with higher accuracy, which is over 89%, which is higher than the models use only one data type. And random forest classifier did help us to explore the feature importance, and we learned district information. Oh, it's just is this spot in district 1 or district 2 into district 7, or traffic characteristics and roadway functional classification are the most important information in crash spot identification. And also using this mixed data model, this routing software companies can recommend safer routes to users to just avoid the dangerous areas. And the government can use this proposed method and data to build roadway safety diagnosis system to establish roadway maintenance system in advance. Let's summarize my presentation. So all my research in Qatar during my PhD is about crash modeling, and it's using statistic modeling or machine learning modeling. But also I did some work in transformation big data analysis, as I showed in the last part, image or even video. And also those econometric models, we can use it to solve some problems related to demand modeling, like mobility on demand or right sources problems. And that will be all for my presentation. So do you have any questions or comments? I know I divided it into 3 parts and 3 topics. It's kind of complicated. So if you have any questions, you can point it to the part first and then ask your question. That'll be easier. Thank you.
And so thank you, Runan. And any questions? So again, let's follow the same format. If you have questions online, you can unmute yourself and directly ask, or you can raise your hand so I can call your name, or you can just leave the question in the chat box. I will be able to share that with the class, and I believe they can see that the chat box message. And also for those in class, if you guys want to ask questions, please raise your hands. Yes, you can say that. I can repeat. Yeah, the questions that in the first section, are you able to look at the illuminance along the roadway? How can you do that?
Oh, you guys can see my slides, right? Or you cannot. Okay. Right. Okay. So the first question is how we can see the what luminous? Luminous? I didn't. Can you repeat the question again? Sorry.
How can you sort of measure the illuminance along the roadway?
Oh, okay. How we collect the data. So here we go. I try to make it clear enough. So let's see, along this roadway, we have our there's a car and our measurement meter is mounted in the car, and we collected it's mounted in 6 feet above the ground, and we generated this point for measurement every 10 feet in each lane, and then we drive through our car and collected this luminous values of these points. And then we calculated the measures I mentioned. That's how we do the collection. If that's clear enough.
Yeah, that's cool. Did you also consider vertical illuminance at all when you did that, or was it just horizontal?
When we did this study, we only consider horizontal, but now we are consider more into vertical because we feel like horizontal probably cannot capture the real risks. Yeah, we are considering the vertical now, but this study is only for horizontal. Yeah.
Thank you. So one suggestion, you don't have to make so many animations with small graphs. You could separate them in different slides. So next time when you make presentations, information would be a lot clearer, and you don't have to blow it up. Next question is from the online audience, Leomar White. And his question is, what were some of the limitations for your hotspot prediction model?
Oh, this hotspot prediction model. So for me, I would consider the limitation is I did not consider the temporal instability, which means this hotspot identification turns to be long-term identification. But I feel like now the roadway conditions change every day with like the roadway construction or any event incident. So if we can do it, if we can get the data more like real time or more like every few seconds or every few minutes to do our prediction or identification, that would be more accurate and that would be more useful for this routing software and for future application. And also in this study, I only included roadway characteristics and traffic data and also satellite image. I feel like it would be great if I can include street view, because street view is how you can see when you are driving, to mount it into that. And those are two directions I think I want to go. And also, so for the model part, I think this combined neural network is good enough, but I'm still looking for like, is there any better models to improve the accuracy though?
So next is from Huiqing Liu. How about the temporary problem about the analysis? Perhaps the elimination condition is not the same as accident happened.
In the first study about this illuminance conditions, we actually consider that. So the reason why I use this 4 years data is for this 4 years data and also for this 440 roadway segments, we selected it because the lighting conditions, the illuminance conditions did not change. Like we did not upgrade it from HPS to LED. So it's all consistent. So we selected this roadway segments. And also for the question you mentioned, this 4 years is the year we collected and generated and also processed the data. So that's why it's not like new data. We also have crash data in the latest 2 or latest 5 years, but I only use like data 10 years ago, just simply because to consistent with other data sources. That's the temporal stability I would consider in this study. Yeah.
Okay, great. Any other questions? Yeah, sure. Some of my comments, right? This is good for this audience because they're not familiar with your work. For your dissertation, you may want to reduce the contents of the first two problems since they have been presented before, while you want to focus on the third components. And you still can. I think one thing that we discussed before was if you're looking to the method of your third presentation slides, you know, can you go back to your data structure?
Oh, here we go.
Yeah, this is not data structure. Data structure is more about, you know, each row, each column, what the data is. Right, you could organize your data almost as a matrix.
Mm-hmm.
I mean, you can include the, it's like a nested, you know, data structure. You have the first portion of the structured data can be easily organized as a vector, and then the image as a array of RGB values can be sort of embedded into this structure, and the output will be, I don't know, the crash. What is output?
Output is
1 or 0?
Yeah, classification. Yeah, 1 or 0.
Right. Yeah. So I think it's better to present them in a more intuitive way. You know, you can say 1 or 0. 1 means safe, 0 means dangerous, or the other way around. And what each column is. I mean, you have that down there in your next slide, right? Next slide.
Yeah. Like the slides. Yeah.
Yes.
I'll reorganize.
So I think it's going to be relative more intuitive to have a hierarchic structure. You know, what data structure means a hierarchic structure. So in input data, under that you have traffic data and roadway characteristics. Under traffic data, you have 3 columns, right?
Mm.
TF act, TF and AADT, you know.
Flag.
And I don't think you need to paste Excel that nobody can see what it is. You know, you just need to explain under the input. There are 3 traffic data, roadway characteristics, and image data. And traffic data has 3 input: TF act. What is TF act? What is TFLG? What is AADT? You can explain them there. And under roadway geometries, you have curve, grade, whatever, you know, for this. And under that, under this image data is what are the pixels, right? So, and you can give these examples, but I think you can better really show the structure of data rather than this kind of a separate presentations. You know, that's what I discussed with you last time. And method data, well, sure. And then you can go to the model, right? Model.
Oh, this way? Or you want it the other way around?
Right. So here, I think you need to clarify what is the model, what is the method, what is the data, right? Right now, what is model, what is method, what is data?
Mm-hmm.
Right. What's your understanding of these different terms?
I consider method as a more general, more big concept. That's why I think through this page, it's all can call it method. But model is just an approach, a quantitative approach to do it. And what the other term? Data? Data.
Yeah. I think right now these notions are a little bit confusing. You know, I would recommend delete method. Just keep the data in the model to make it simple. All right. Because
Okay.
you can say every slide you're talking about is about method, which is you know, not particularly helpful in understanding the problem. And also, you go to method performance matrix. You know, you didn't explain what NC and TPC, whatever this is. Please provide the detailed formulation based on your data format.
Okay. Okay.
All right, so these are my suggestions. I thought I had them before. You probably didn't have time to incorporate them, but you can incorporate them later. Just to you know, we need some depth and clarity when we make a dissertation presentation, right? I hope you can put your depth on this particular portion of the work that is new to what you presented before. Yeah. Yeah, that's all the comment I have. You know, I'll be happy to share with my comments from the perspective of your dissertation defense for students. And you know, if you guys have future presentations like dissertation defense, you're welcome to register in this Friday Transportation Seminar Series presentation, and we will give you this opportunity. In the end, let's thank Runan again for her presentation. Yeah, some applause.
Thank you, everybody. If you have formal questions, you can email me on my USF email.
Yeah, sure. If you have questions, please feel free to contact her. And next presentation will be from FHWA Sexton Lab. They're going to talk about their recent development on connected automated vehicles, particularly the Karma cooperative driving automation ecosystems, including infrastructure, vehicle, and cloud computing. And thank you again. Hope you have a good weekend. Bye-bye.